Hi, and welcome again to my Physics Online video lecture series. Today's video we're going to be looking at interpreting RC graphs. This is a follow-up to the last one that I made in which we also discussed RC circuit graphs, but in the last one we discussed it from the perspective of just looking at what shape the graphs made for voltage drop, for current, for charge stored on the capacitor, that kind of thing. And we looked at how changing some of the parameters would affect not so much the shapes as maybe like the discharge times and whatnot. The maximum height that it charges to, the maximum current, the rate of discharge, all that stuff. So in today's video we're doing kind of the complement to that, which is that I am going to just generate a graph, and then from that graph we will try to interpret what kind of parameters we may have. Sorry if there's a bit of noise coming through. Last time when I made one of these videos, the window washer came by and washed my windows behind me. Today we have the groundspeople mowing the lawn in the window behind me. So I don't know how well the microphone's picking that up. In any case, let's open up our plot generator. It's a very slightly different program, well, same program, but a slightly different set of code than what I used on the last one. The last one, I used this RC circuits quiz graphs. Today I'm using RC voltage plots, which just simply plots voltages. The difference basically is just that I have this set up a little bit differently than the other one. This one right here, everything is determined in terms of R and C and epsilon, and basically the time steps and the maximum time are determined in terms of R and C, the decay time tau. Today's video, the main difference is that I have fewer plots that are being generated, just simply voltage, and everything is now generated rather in terms of the half-life rather than tau. And we can look at a little bit of both as time permits. So basically what this code does is it lets me sort of declare, do I want to see the voltage on the resistor, on the capacitor, or both? And it lets me declare whether I want to have a charging or a discharging circuit. So that's what these two lines are doing. All of these ifs and else if kind of statements are basically just to set all that up. They're basically just reiterating a simple line of code that says plot this, plot that, don't plot this, don't plot that. Or really just plot this and plot that, and the don't plots are just that line isn't present if I don't want it plotted. So type 0, what plot 0 basically means that I'm expecting to get a voltage versus time for the capacitor when it is discharging. So you can see the parameters I'm using here, and as a first example we'll just allow you to see all that. Basically in this one, rather than giving you R and C, I've defined a tau and I've defined a half-life. And so I've defined the half-life to be 2. That specifically means it's going to be 2 seconds based on how I've set up the code. And then tau is found in terms of that. I've also set a max voltage of 8. So if I were to make this plot, I should get a decaying graph with a half-life of 2 seconds. And that is indeed what I see here. So I start from 8 volts. I'm decaying. After one half-life, this is 4 volts, that's half of 8 volts. That occurs in 2 seconds. Okay, a second half-life means 2 half-lives have passed, means we're at a quarter life, means I should be at 2 volts, and that's at 4 seconds. So that's the basics of what we have in this code. So what I'm going to do is I'm going to kind of drop this plot into my little presentation, I'm going to draw a sort of reminder of what this circuit basically should look like. We expect, in this case, to have a resistor connected to a capacitor. There may be a switch, for example, that closes at time t equals 0. We have resistor, we have capacitor, and we basically have delta VC at t equals 0 is, in this case, 8 volts. And we can see that on the graph because here's time 0 and here we are at 8 volts. Reminder, the equation that we expect for this is delta VC is delta V0, so this would be delta V0 times e to the negative t over tau. And our other reminder from a couple videos ago, we got an important result that the half-life, so t1/2, is the decay time tau times the natural log of 2. And similarly, the quarter life is tau times natural log of 4. Eighth life is tau times natural log of 8. The 1/nth, let's say, life, let's make this a capital N, would be tau. This is a tau, not an I. This is a tau ln n, where whatever this number is, this is telling us the amount of time to drop from initial value to 1/n of the initial value. Okay, so coming back over here to this graph, this right here would be my half-life point right here. Delta VC is 4 volts, which is 1/2 of 8 volts, and so T is the half-life value. So from that, I've been able to determine a half-life. I can also do that for other things like quarter life or eighth life. So this right here would represent my quarter life. Here's delta VC is 2 volts, which is 1/4 of 8 volts. Again, this 8 volts is our initial. And so this means that T is T1/4. Okay, basically what that means is that for this graph, we've determined that T1/2 is equal to 2 seconds, and T1/4 is equal to 4 seconds. And that matches from the code that I showed a moment ago. From this, we can basically determine a value for tau by rearranging these two equations. Tau should be T1/2 over ln2, or it should be T4 over ln4. So using tau is equal to T1/2 divided by ln2, I get 2.88, I think it's a 54 or something like that, seconds. And so with the precision that this graph is allowing, I would expect to maybe round that to like 2.9 seconds roughly. And so that's somewhere in this vicinity right here. And so if I pull up from here and I pull over from here on the graph to analyze, I ask, is this value here 1/e times 8? And so 8 divided by e is about 2.94. So 8 volts times e to the -1 is about 2.9 volts. And looking here, we are pretty close to midway between 2 and 4, so this is credibly 2.9 volts. Okay, so that's like the most basic level interpretation of this graph. We can usually do more with it than just that, though. And before we do that, I'm going to give you just a simple graph, and I'm going to say, can you figure out what the initial voltage on the capacitor is, and can you figure out what the initial voltage on the resistor is, and what the tau value is. So let's get a graph. So here's my graph. Again, we're assuming it's discharging, and so can you figure out what tau is from this graph and what the initial voltage is, and for that matter, what the graph for the resistor would look like? Note that the graph for the resistor, when I plot it, will have a minus sign in it because of how Kirchhoff's rules look like. So that just means you can always flop the leads around. So think about what you expect those two to be. Maybe take a moment to pause and figure that out, and then hit play when you're ready to check your answers. All right, the plot of both will look like this if you're doing voltages and time. Now, granted, I've rescaled the y-axis because, again, I have a negative value here for the voltage drop across the resistor. Another way of looking at it is that the resistor will look pretty much identical to the capacitor's voltage, but in reverse. Now, the other two parts of that question were, what are the maximum voltage across the capacitor, and what is the half-life, or the tau value, I mean. So this right here is the initial voltage, because this is where my voltage is starting from. So essentially my delta V0 is 12 volts. That means that half of delta V0 is 6 volts. So now let's look for where 6 volts occurs on this graph. Well, that's this right here. This is 1/2 of delta V0. So we just follow this line along, and then we follow it down, and we see that the half-life, therefore, is again 2 seconds. So T 1/2 is 2.0 seconds. And that means that tau will be that half-life, T 1/2, divided by the natural log of 2. And so that's 2 seconds divided by natural log of 2. That gives us, again, about 2.9 seconds. Okay. Now, a more interesting example than just that, I think, is to have a graph, and note that stuff has changed here. So we have a graph, and we're told what the value of the capacitance is, and asked to figure out what the resistance, the maximum current, and the Q0 are. So our process is pretty similar to what we've done on the previous one. We just add some more steps. First, we have to use the graph to determine delta V0 and tau. Same process as before. The slight wrinkle, of course, is that the half voltage is 10 volts, doesn't fall nicely on the grid. But if you go to the quarter voltage, that's 5 volts, it does fall nicely on the grid at 6 seconds. So the quarter lifetime is 6 seconds. That means that we should be able to determine the tau, the decay time, from this quarter life by using quarter life divided by ln4. So we're looking at 6 seconds divided by natural log of 4. And what that gives us is about 4.3281 seconds. So we'll call it 4.3 seconds. Now we can use the time constant and C to get the value for R. Tau is RC or CR, so R is tau over C. That's 7,869, so we'll round that to 7,900 ohms. Step 3 is a little more complicated. We have to use Ohm's law, that is delta V sub R is I times R, and our knowledge of this graph and how it's related to the delta V sub R graph to get Imax. Essentially, this means that we're using delta V as IR, Imax is delta VR max over R, and delta VR max is delta V naught. this gives about 2.5 milliamps. The last step to solving the problem that you've been given here is to use the definition for capacitance and the maximum initial voltage from this graph again to basically figure out what the initial charge is on the capacitor. So that definition for capacitance again is C is defined as charge stored divided by voltage drop across the capacitor. And so you can get that the charge must be the capacitance times the voltage drop, or in other words, that the initial charge must be the capacitance times the initial voltage drop, which again we know is 20 volts. So that means that Q naught we expect to be 0.55 millifarads times 20 volts. Now you could convert this millifarads over into farads and get an answer in coulombs, but since you have a milli here and no unit modifier here, your result will actually be in millicoulombs. So you multiply these two guys together, you get your 1.1 millicoulomb initial charge. So that's it for interpreting a discharging graph for the RC circuits. That's some set of ideas for it. There is, on the other hand, also the charging graph. So we can briefly look at that as well in this video. So what I have right here is the plot assuming actually similar parameters to what we had on these previous graphs. So going back up, I have this plot of a discharge from 12 down to 0. This is sort of the counterpoint to that. What if I plug into a battery with EMF 12? So this is charging up to 12 volts. And how do I know that it's charging to 12 volts? If I extended this graph some more, then this would basically be asymptotic to 12. As for how I know that it's going to 12, that takes a little bit of discernment when you're not quite at the asymptote point yet. But one way to do it is to understand how half-life and quarter life works for these graphs, or general 1/n lives. So half-life should be the amount of time that it takes to get from 0 to halfway up to whatever you're charging to. So if I'm charging to 12, then my half-life would be right here at 6 volts. So 6 volts, this would be 2 seconds. I expect this to be my half-life since I expect to be asymptotic at 12. So this basically means my EMF is 12 volts. This right here would be delta VC equals 1/2 of that EMF, and that gets me my half-life. Now, the quarter life basically means that I need to get from halfway between this point and the asymptote. That means basically 3/4 of the way there. Well, that would be 9 volts. So this right here, let's actually switch colors, but this right here would be 3/4 of the way there, 9 volts. And sure enough, 3/4 of the way there happens at 4 seconds. So T 1/4, basically this is 9 volts, 9 volts being 3/4 of 12 volts equals 3/4 of the EMF. All right, and since that worked out, and again, I kind of deviate upward a little bit with this little line that I drew. Since that works out, I know that I must be approaching somehow to 12 volts. So it takes a little bit more discernment to figure out what is quarter life, half-life, that kind of thing. After that, the interpretation is basically the same. Once you have quarter lives or half lives, you can use it to get tau. You can also try to get tau directly. It should be 1 minus e to the minus 1 times 12 volts, but you can see why picking halves and quarters might be a little easier to do visually. But the process after that remains the same as the process we used here. Basically, you use the graph to get delta V naught, to get tau from possibly half-lives, quarter lives, or whatever. And then you can use tau and either C or R to get whichever one you don't know. So if you're told that this one right here has a value of R equals 2,000 ohms, then you'd use tau and R to get C. And then you can get maximum current, you can get maximum voltage on the capacitor. Again, if I were to go into this program and replot, instead of plotting just the capacitor voltage drop, if I add in the voltage drop for both, whoops, I messed up where my line is that I needed to change though. It's that one. Then I end up with this plot right here, and sure enough, I'm starting from 12 and decaying down to 0. So actually, the interesting thing about the half-life is it's also the point at which both of these graphs will cross each other, and both will have, as a result, the same. So if you're given both graphs somehow, then it's really easy to find where the half-life is. But that's kind of like neither here nor there. Going back to this, though, the process, once you've determined a half-life, a quarter life, an eighth life, some convenient value to get tau, after that it's pretty much the same as the process that I used on this discharging graph. Now there are some variations to all of this. For example, instead of being told resistance or capacitance, you may be given the graph and then told the initial charge on the capacitor is this number, or maybe you're told the initial current is this number, or the current at some time is this number. So that's just a variation that throws in a change in this second step. So originally the second step is use T and C to get R, or use tau and R to get C. Your new second step, it's like an intermediate step to step 2, would be, for example, use the voltage graph and that current value and Ohm's law to get a value for R. So what that might look like is this. Let's say that you have this graph right here, and you're told that the current after one half-life is 2.4 milliamps. And so now you got to determine R and C. So, the process is similar to what we've done, where you first have to get this half-life, which we found was 2 seconds, as it turns out, or 2.0 seconds if we want to keep some semblance of sig figs. So to get the R and the C, basically you do this. Use Ohm's law. You know now that R in this case is delta VR at this time, which is 6 volts, so 6.0 volts divided by your 2.4 times 10 to the minus 3 amps. And so you're using 6 volts because that is the correct voltage at the time for which you've been given the current. And so this gives us a value of R of 2,500 ohms. Okay, well now we have R, so finding C is just a matter of rehashing the step 2 from the previous. Basically you use tau and R to get C. So basically you're using tau is T1/2 over ln2, so that's 2.0 seconds over natural log of 2. I believe that was 2.9 seconds. Yeah, 2.8854. So we'll round to 2.9 seconds. You can retain the digits for the calculation. And so that means that C, since tau is equal to RC, C must be tau divided by R. And so C is 2.9 seconds divided by 2500 ohms, which gives us a value of 1.15 times 10 to the minus 3. So we could call that 1.1 millifarads. So that's your basic process. And you can essentially combine these in a variety of ways to get your whatever you're looking for off of these graphs. Like maybe you're given the voltage across the resistor instead of the capacitor, what have you. It's just different variations of the same basic process that I've outlined, using the graph to get a tau and maybe a V naught, using tau and either R or C to get whichever one is unknown, using R to get current or using current to get R, using C to get charge or charge to get back to C, depending on what you've been given or not given. And of course you can figure out power from P equals I squared R, or energy stored from U is 1/2 C delta V squared, etc. So that's really it now. That's all that I wanted to do in this video. So hopefully it helps you out, and thanks for watching.